Hi guys, this is the explicit discussion notes for the Chemical Physical Change ADI lab. The purpose of this is to make sure you feel like you have enough background information to make sure you're comfortable with your group's claims, to know if you need to get more data, and then or to help you get ready to start writing the paper, which we'll talk more about shortly. Okay, so first off, let's talk about matter. First off, you see a little delta sign, a little triangle. That means change. We use it to abbreviate. It's often an abbreviation we use in the notes. So, all right, matter is anything that has both mass and volume. Okay, so things that are matter, water, stone, but one that often people think about, forget for whatever, is air. The air is an example of matter, because air does have volume and takes up and has mass. You don't believe me? You weigh a balloon empty, you blow it up, and you weigh it again. It's now filled up with the volume has now increased, and you stick on a scale, and it's going to weigh more. Okay. So the three main states of matter that we deal with on Earth: solid, liquid, and gas. Yes, there's plasma, and there's a couple other weird ones, but the ones that we deal with in class are solid, liquids, and gases. No plasma in my class, please. They all have to do with the arrangement of atoms in the material, how quickly they're moving. So solid, the atoms are moving a lot slower, gas are moving very quickly. But anytime you have a change in state, we call that a phase change. Okay, a phase change is a change of state. So all matter can be in any of the solid, liquid, or gas in each state. And actually, there's some fun ways in which they sometimes move from one to the other. You don't actually have to go from solid to liquid to gas. If it's getting colder now outside, you get ice cubes. Think about ice cubes in your fridge. If you remember to look at this, you put ice cubes in now, in a couple of months, if you look at them, they actually gotten smaller. They get smaller. They kind of disappear over time, and that is because they are able to do. Wow, the term just went right out of my head. Sublimation. They're able to do what's called sublimation, is where they actually can go directly from solid ice to gaseous water and skip being a liquid in between. Has to do with the constant opening and closing of the freezer and the airflow coming in and the temperature there. But it's kind of fun that you can actually mess around. Again, some more advanced chemistry to spend a lot more time talking about. There's a whole chart and everything. Okay, so physical properties. We talked briefly about this in the background information for the lab, but let's get into this a little bit more. So physical properties are useful to identify and describe and classify matter. And biggest thing is they are the characteristics of substances that can be observed using your senses without, changing the substance into something else. So what you start with, you end with. Chemical properties, none of these are all, you can observe these without changing what it is. So examples of this: size, shape, freezing point, boiling point. So like size and shape, if you take a block of ice and you break it in half, it's now got a smaller size, but it's still a block of ice. Freezing point, boiling point, melting point. If I freeze water, if I boil water, if I melt an ice cube, they're all still water. Magnetism, viscosity, density. Density is mass divided by volume, so it kind of matter. But the density of 1,000,000 pounds of aluminum at room temperature is the same density as a half a gram of aluminum at room temperature. That's a property, it's a physical property. Luster is kind of apparent shininess. Like gold has got high luster. Viscosity, I love talking about viscosity. Viscosity is how well something pours or how quickly it kind of pours. So low viscosity, water, rubbing alcohol pours really quickly, while high viscosity stuff like honey or maple syrup pour really slow, especially if they're cold. You can also have stuff like hardness, so like diamond's really hard and carbon's really soft. Texture is what they feel like. Color. Okay, now this is a big one. You ever seen I have a gold ring. My wedding ring is gold. It's got that gold color. If I took my wedding ring and pounded it into a penny shaped thing, it would still look like gold. It has the same color, even if I changed the shape or if I melted it and poured it somewhere else. it still has that same gold color. Odor, be careful if you're still in class. Remember to waft. But no, I'm not going to talk about the smell of gold. But the smell of things like ammonia, which is a chemical, or bleach, that's the smell of those. You can tell it by that. Taste, don't taste stuff in lab. But sugar tastes like sugar, whether you have a lot of it or a little of it. Temperature, I don't know why I have that one on there. Ignore that one. So chemical properties. Chemical properties are a little different. So chemical properties are characteristics when a substance interacts with another substance to change its chemical makeup. So this is to determine to test a chemical property, the act of looking at or examining or testing the chemical property changes what the chemical is. So examples of this, flammability. If you take gasoline or a piece of wood, those are flammable. They will light on fire, but when you're done, you no longer have gasoline or wood. But its ability to catch on fire is a chemical property, flammability. Rusting, iron. Iron, if you leave iron outside where it's wet and there's lots of air, iron will rust. You go from shiny silver iron to flaky, soft, yellow or orangish colored rust, iron 3 oxide. I'll point out that you go from going from a shiny metal, I don't know what I'm trying to draw here, shiny metal to flaky rust, that is a chemical property that things can rust, and part of the way you can know it is you have a change in the physical properties. Creating gas bubbles. If you mix chemicals together and they make bubbles, that's telling you something. And not every chemical mixes together and makes bubbles. It's a chemical property. Creating a new chemical product. Knowing that if you take hydrogen gas and oxygen gas and you light them on fire, you get water. You're creating a new chemical product. Those are properties that when you burn hydrogen in the presence of oxygen, it creates water. Reactivity with water. Some things you put them in water, and I'll show you this in class at some point. They fizz and they run around and they bubble and they can catch on fire. And some you put it in water and it just sits there. pH. pH is a weird one. Be careful because it's more about change in pH. Is a chemical property like this. pH will go from this to this when you do this to it. So don't think of it like, oh, it's got a pH of 3. That's the chemical property. No, it's like, oh, it has a pH of 3, and now we've added some stuff to it. Now we have a pH of 7. That's more about the chemical property. So, putting this all together, chemical properties are things you can observe without changing the identity of the product. It's the same thing when you're done looking at it. Chemical properties are not observable without changing the identity of the compound or of what you're looking at. It's not the same. You take a piece of toast, you take bread, you make a toast, it can never be bread again. Okay? But the proteins in the bread are capable of browning when adding heat. That's the chemical property. Okay, so chemical properties and physical properties are useful for determining if you have chemical change and physical change. So remember, a physical change changes the substance, so there is a change, but it does not change the identity. It does not change what it is. So going from ice, it's my favorite example, sorry, because it's really straightforward. Going from ice to water is a physical change because it's still H2O. Chemical changes occur with changing the identity. You start with one substance and you end up with another one. Normally, one way you can do that is the physical properties change, right? Think of that rust. Shiny metal iron has certain physical properties. Its appearance, what you can do with it, it can form things and it's strong and it's harder and it's shiny. And you have a chemical change, you get a chemical change, and now you have rust, which is flaky and soft and different color. All of those you've changed the physical properties, okay, by seeing one of the chemical properties. So, one more time. Physical changes occur when the appearance of the substance change, but chemically the substance is still the same. The individual molecules do not change. So with this lab, you need to be thinking about, okay, did you see something change, but how do I prove if it's still chemically the same or not? Because a chemical change occurs when the atoms making up the matter rearrange to form new substances with new properties. Okay, so the physical properties change, or the chemical properties change. Think of it this way: wood is flammable. The ashes you get when you burn a piece of wood, I didn't make charcoal, is not flammable or has a different amount of flammability. Okay, you've changed it so, and besides going from looking like wood to looking like a bunch of black powder, which is a change in the physical properties, you change the chemical properties because it went from something that is flammable to something that is significantly less flammable. So, evidences of chemical change. Remember, I told you that delta was coming up. These are some things that you get evidence of chemical change. Okay, these are mainly things that occur in a chemical reaction. Most chemical changes occur in a chemical reaction. You don't see all of these. Different reactions do different ones. So let's go over a couple of the most common. Okay, first one, evolution of a gas. By the way, I will upload this as a video as well as a PowerPoint. Go through and watch the videos. They're really, it's better than just me talking. You know, I talk a lot. Evolution of a gas. So this is not like the same thing as, you know, you put water on the stove and you boil it and you start seeing bubbles forming up. Okay, this is you mix chemicals together and you get the formation of a gas. Okay, you're forming a new compound. You're forming something new that is actually literally bubbling away in the air. That is evolution of gas. That is an example of a chemical change because it's a chemical reaction, which is a changing of the chemical and physical properties. Precipitate, formation of a precipitate. This is one that always throws kids when they don't understand. So what happened, the forming of a precipitate is we're talking about you're taking like two liquids and you're putting them together and a chemical change is occurring and you're making a substance with a new property, and that property is it is not soluble, it does not dissolve in water. So you end up with something that starts a precipitate, which is basically a solid that's going to, we say it falls out of solution. So like this stuff that we're mixing, this making this orange over here, or yellow, you let it sit for a little bit, eventually it's all going to settle down at the bottom of the beaker. It's settling out. Okay, you often hear precipitate in close to stuff like precipitation, you know, rain, where you know it's in the cloud and it falls out of the cloud. Okay, please note, this is a solid, but you're not suddenly forming a rock in the beaker. Okay, you're forming particles that are solid that no longer dissolve in water, and they're settling to the bottom, but that doesn't mean they're still mixed with liquid, so it can be a little slushy. But you get something that's got new properties that look different. There's a color change. It's a solid instead of two liquids or stuff dissolved in water. Those are all examples of evidence of a chemical change. Production of heat or light. If it makes a lot of light, it's a chemical change. That light had to come from somewhere. It's a type of light is a form of energy that transfers out. Production of heat, be careful. This is not, I say production of heat, but and so most people immediately go, okay, it's hot, which is true. So if you suddenly have a bunch of if something gets really hot and starts glowing, or just gets really hot, that's probably that's evidence of a chemical change, of a chemical reaction. But it can be actually the other way. Some substances, when you mix them together, they actually cool off. It's a different type of chemical change. Instead of being exothermic, it's endothermic. We'll learn about those. So basically, you almost think of it as a change in temperature without you adding more energy into the system. So you're not heating it up on a Bunsen burner or a hot plate. You just mix these two things together and you have increased heat or light. Remember, you don't always see all of these, so they all kind of, you know, you can kind of get different combinations. Watch the video. Change in color. Definitely watch this. That's my favorite video. Change in color. This is, it can be like the precipitate, because you saw the video, if you look at the video, it's precipitate. You're mixing two clear things together, you get a yellow precipitate. That's also, besides being a precipitate, Let's just say the word precipitate. Besides being a precipitate, it's also yellow, which is not a color you had before. So this is the video is actually cool because it shows what's called the iodine clock reaction, where you have clear solutions becoming black. Sudden color change. This is evidence of a chemical change because it's the evidence of a chemical reaction. All right. All of this, though, please remember, this comes back to the law of conservation of matter. We talked briefly when we talked about energy, the law of conservation of energy, and I mentioned that the law of conservation of matter is related to the same. You can't create or destroy matter. All of these, we're not making new matter, we're just rearranging it into a different form, okay? Law of conservation of matter is pretty fundamental to the study of chemistry, okay? Matter is not created or destroyed, only transformed. I like to think of it as Legos. Let's say you have this bunch of little Legos and you make a pretty red car. Yay, pretty red car. Now I'm going to take all those Legos apart and I'm going to put them into a pretty red boat with wheels. Must be a tugboat. Okay, so you can take a car and rearrange the pieces and make a boat using Legos. You're not magically making new Legos. You're not suddenly making new Legos appear out of thin air with completely different shapes. You're rearranging the pieces that you have. That's the law of conservation of matter. You cannot create it or destroy it. You can only rearrange it. You can only transform it. Keep in mind, I'm going to keep harping on that, come back to law of conservation of matter. The sooner you get it, fundamental concept in chemistry. You're going to talk real briefly about pH, and then you will be done. Okay, so I mentioned pH at the beginning of the class, or at the beginning of the unit. Just so you know, pH stands for the power of hydrogen. Please notice also a lower P, H being a capital H. People always put in the paper like pH or pH. No, those are wrong. It's that. Okay. It goes from 0 to 14. Actually, there's some cases we can go into the negative, which is crazy when you learn more about it. But just remember, the P stands for the measurement of hydrogen ions. So this is the concentration. That's what we call this little brackets. It means the concentration there. For your purposes, for the purpose of this class, it basically means the more hydrogen you have, the more acidic. The more hydrogen ions you have, the more acidic the solution. So, couple of key numbers to remember. If we have something that has a pH of 7, we say it's neutral. Okay, it's got a balance of hydrogen ions and hydroxide ions. Those are the two things that mainly make up acids and bases, or strong acids and bases. So anything less than 7 is considered acidic. So you see, battery acid, lemon juice, vinegar, soda. So they say soda rots your teeth. It's not really the sugar that does it; it's the acid. Basic solutions, pH are greater than 7. So here's the thing: people are like, "Oh, acids are bad, bases are big." Bases are a big deal. This is bleach. You see what that does to your clothes? It's the same thing that acids do. So they're basically like two sides of the same coin. Really strong bases are going to mess you up just as much as really strong acids. They're just going to do it in a slightly different way because they're about the hydrogen ions. We'll get more into the acids and bases later this year. Acids, every acid-base solution contains hydrogen ions and hydroxide ions, and so in acids there's more hydrogen, in bases there's more hydroxide, and if you have an equal amount, this substance is neutral, so it has a pH of 7. By the way, at some point you learn it's like we can measure the pH, which is about hydrogen, but they also measure sometimes the OH. Don't worry, we're not doing it. This is more information. And also acid base is kind of like the Richter scale. You might have heard about that for earthquakes. Every step, a 1 to a 2 to a 3 to a 4, is actually a logarithmic scale. So it's going up by 10. So 10 times greater, 100 times greater, 1,000 times greater. Basically, just know the lower the pH, the higher the concentration of hydrogen ions. And so that can tell you something what's going on because with acid and bases, with pH, remember I said it's not necessarily a chemical property unless you see it change. Changing pH tells you that something is going on because if it's acidic and it's basic, where are those hydrogens going? If it's basic and it's becoming more acidic, where are those hydrogens coming from? Okay, something has to be going on, something has to be happening for the pH to change. Okay, so hopefully you feel comfortable with this information. The idea is the next steps for you guys is to start looking at your data and seeing how strong and the feedback you got on your argument poster, and start really thinking about how confident am I in the claim that I have? Do I have enough data that I have collected? Please note, I expect you to collect the data. I don't care about experiments that you saw your middle school science teacher do in class or that you did in middle school. I only care about the data you collect from the labs in the back of my classroom. Okay, so that is the data. So if you have some like, oh wow, I didn't check that. Well, guess what? The labs are still set up in the back. Go back and do it. Okay. So the next step we'll start talking about in the next class is once you're comfortable with your claim and you're comfortable with your data and you think you understand why your claim is correct or why you should think your claim is correct, then we got to start writing a paper. If you're go-getters, good for you. Please note that there's a rubric. I've changed the rubric a little bit from the one that's currently in your OneNote. I'll get the updated ones out on Tuesday or in the future if people are. There's a new one. You can start looking through it though. All I did was take the one that I already had and kind of rearranged it and condensed it a little bit, but all the same stuff is basically there. So we'll spend more time talking about that. All right. Good luck. And yes, I'm sitting in a car recording this video because it's been a long weekend and I had to move and I couldn't get into school. So it's weird, I know. Just go with it.